In this video, I'm going to talk about optimizing BARC thickness. This is something that people commonly want to do with a simulator. In this approach that we're going to take today, we're going to use HyperLith to optimize the BARC by varying the BARC thickness and looking at the profile of the resist. Now, if you just set the thickness as a variable, tBARC, and give it a range, let's say 0 to 100 in steps of 10, so that'll give us 11 values, and then simulate, there's going to be two problems with that. First, I'll put them all on one plot. So the problem is that as you change the thickness of the BARC, we really need to redose to size. Just incidentally, I'm using the trim resist model here. So it's just a thresholded resist image. So the two problems again are that we need to redose to size every time we change the BARC thickness. And the second problem is as we change the BARC thickness, our coordinates are changing here. And so some resist profiles are lower and higher because the coordinates are changing. So you can see here that as I move the BARC, the resist profile moves up as I make the BARC thicker. So both of these can be easily handled. So on the wafer and resist, what we're going to do, instead of saying that the BARC thickness, we'll leave the BARC thickness like this, but what we'll do is we'll add another layer. Sorry, we don't need a variable here. We'll add another layer under the BARC, insert below. We'll give it the same N and K as the substrate. And we'll make its thickness 100 minus tBARC. This way, this layer picks up the slack. So when we move, for example, to BARC 40, okay, then we get that this thinner layer here, we'll call this substrate fill. Okay, so as the BARC gets thinner, this substrate fill gets thicker. That way our resist coordinates from the bottom of the resist to the top of the resist are in the same position. So now when I simulate, I'll see them all at the same position. Okay, now the next problem is that we need to redose to size because basically we don't know the optimal dose for each BARC. That can be easily handled with our multi-dose. So we designate tBARC as a trigger variable which triggers a dose to size, or a redose to size for every change in this variable. So now we have a special nominal dose for each value of that variable. Now when we simulate, they'll all be, you see where the Z measure is here. Let's go back here. We're measuring down here. So we expect all these profiles to be dosed to size correctly at Z measure. So now we go to FEM control, or sorry, data and results. We plot our profile again. Okay, so now we've got all the profiles. You see how this inflection point here, they're all pinned there because we're all dose anchored there. So now what we're going to do is let's plot them on separate plots. And this is a nice little feature that you can scroll. If you use the right and left arrows, you can look at all the different conditions. So we see that it's somewhere in the range of 30 to 50 seems to be our optimum. So let's narrow our range here from 30 to 50, and let's just go in steps of 1. Again, we have to dose to size. And we'll threshold to size, even though that shouldn't be affected by the BARC thickness. And then when we simulate, we're going to get all the profiles for thicknesses of BARC 30 to 50. Put them again on separate plots. And now as you scroll with the right arrow to the different settings, you can pick out the best one. And I would say that looks the best. So 42, 40, so our default value of 43 is pretty good. I would say maybe 41 or 2 might be better, but it depends. This is just for this particular pattern. Now, other ways to optimize the bark are to look at things like CD versus bark thickness, or the total energy reflected from the bark, or just reflectivity at a single plane wave, maybe normal incidence. But I prefer this method. I think this is the best way to optimize a bark, because in the end, you care about the profile of your pattern.